Okay, so in this problem, we're taking we've got a function. Let's see, x cubed plus 3y squared. Okay, so we've got some function now. Let's see, the domain is some rectangle over here in the xy plane, and we've got some function up here, whatever, some surface. We're computing this volume. Okay, so evaluate the integrand a of x for that single variable integral. So what's single variable integral? Well, the problem says we're computing this volume with a single variable integral with respect to x. In other words, x is going to go from 2 to 3 for any given value of x. There's a corresponding cross-section. Let me draw the cross-section with the bigger pen here. There's a corresponding cross-section, and that cross-section has an area, and that area is a of x. And with that, once you can compute that a of x, you can write that the volume in question that you're trying to compute is a single variable integral a of x dx, right, where x goes from 2 to 3. Right, so this is kind of, the way we turned this volume problem into a nested integral was a two-step process that was started with viewing the volume as a single variable integral like this. So the problem wants you to figure out what is that, right? Evaluate that integrand a of x for this single variable integral that you're using to compute volume. Now, so we'll talk about that in a second to evaluate the integral. We've already kind of done the next part of what's the domain for the single variable integral. Well, here it is. X goes from 2 to 3. Is that cool?
Got that.
Yeah. Okay. All right. So let's compute this. So what is this a of x? Well, that a of x. Now, this is also, if you go back in through the section, when we were developing, why volumes can be computed with these nested integrals. We did an example where we computed one of these areas, and the point is that this integrand here is for that particular value of x. There we go. For that particular value of x, we're looking at a cross section, and we want to compute the area under that cross section curve. So area under a curve. So in fact, this a of x is itself an integral. Right? It's an integral where we're going in the y direction, and y is going to range over certain values. Let's see, this is from 1 to 5. Is that cool? And let's see here, it's an integral of height. Well, height is just the value of the function. It's f of xy. It's x cubed plus 3y squared dy. So now this, when you just look at this expression, you think, oh, it's an integral, so it's just a value. But it's not. It's a function of x. Because if you put in, as far as the integral is concerned, this x is a constant.
Okay.
But it's a constant that, can change independent of the integral. Right? So for some values of x, you put whatever value of x you want, you put that in there, you evaluate, you get some answer. Put in a different value of x, this becomes a different constant, and then you again evaluate and therefore get a different answer. So ultimately it's a function. And then you're just going to evaluate this, and it's going to be some formula involving x. That'll be a of x. Is that cool?
Okay. Okay, then for part 3, you just want me to do them separately. So like in part 2, we'll just do reverse, right, in terms of y.
Let's see. Wait a second. Part 3. What part 3?
Sorry, question 2. As I should say.
Oh, okay. Let me. Is it related? I guess. Let's see here. Oh yeah. Oh yeah.
Okay.
Yeah. So with part 2. Oh yeah. I just did it. In problem 2, what you're going to do is you're just going to do your slice in the other direction. So here, we want to compute this same volume, but this time it's an integral with respect to y. So we're going to have y going from 1 to 5, and then for a given value of y there, we're going to look at a cross-sectional area like this, and that's got some sort of an area, and that's the area that you multiply by dy. So that's, what you might call a of y. Yeah, oh, there we go. Does that make sense?
Yeah.
Yep. Okay. And then so, same sort of thing. You want to write the volume as an integral dy of some function of y that indicates this cross-sectional area. Find what that integrand is and observe that the integral goes from, well, it'd be 1 to 5 instead of 2 to 3. Yeah. Okay, cool. So that was both 1 and 2. Okay, let me stop the recording. It was a twofer.